page 3 of trig equations and identities. Okay, so we have a strange looking problem here. It doesn't just say, oh, what are the x values when sine of x equals something? It is in a weird form. What we want to do is we want to rearrange it so that we have sine x equals blah, blah, blah. We want to have sine x by itself on the left and everything else on the right. So let's do the algebra first. We're going to add square root of 3 to both sides, and then we'll get 2 sine x equals positive square root of 3. Now we got to isolate sine x further. Let's divide by 2 for both sides. If we divide 2 by both sides, then we'll have sine of x on the left, and then we'll have square root of 3 over 2 on the right. Now we have it kind of like we did on the previous page with tangent of x equals 1, right? Okay, so now that we know that sine of x equals square root of 3 over 2, we know from memorizing special angles that there are solutions to that. We want all the solutions between negative 2 pi and 2 pi. Okay, well, at least the solutions between 0 and 2 pi, we can figure those out, right? We know that there is a solution for sine of square root of 3 over 2 here and here, right? So the first, the triangle here is going to be pi over 3, right? And the second triangle is going to be 2 pi over 3. Okay, and so those are two solutions for angle x's which have sine values of square root of 3 over 2. Okay, now we want to know, are there other possibilities but in the domain negative 2 pi and 2 pi? So we basically have memorized all the solutions between 0 and 2 pi. So what we need to do is see if there are any solutions between negative 2 pi and 0. And in this particular case, we can generate those solutions by subtracting 360 from both of these solutions, right? So if I subtract 360 from 2 pi, if I subtract 2 pi, I would get 2/3 pi minus 6/3 pi, which is the same thing as 2 pi, right? And so I would get negative 4/3 pi. So that's another solution, which is between negative 2 pi and 0. What about subtracting negative 6/3 pi or 2 pi from pi over 3? I would get negative 5/3 pi. Okay, so those are also two angles, which actually these angles are the same thing as pi over 3 and 2 pi over 3, because whenever you add and subtract 360 to an angle, you get the same angle again. Okay, and all I did was subtract 360 from each angle. Okay, so those are my four angles. These four angles in the x column are my solution. If I wanted to list them, I would just make a list with separated by commas, but I'm not going to do that every time because you understand, right? If you want to, you could put them in brackets, but you don't have to. Okay, part B, same thing. We want to isolate the cosine x, so we're going to subtract 1 from both sides. So first thing we're going to do is we're going to have square root of 2 cosine x equals negative 1. Then we want to further isolate cosine x by dividing both sides by square root of 2. So I end up with cosine of x equals negative 1 over the square root of 2. Remember, this is the same thing as negative square root of 2 over 2. Okay, what triangle is that? This is a 45-degree angle. It's related to the 45-degree angle, except the cosine is negative. So that means the x coordinates are going to be negative. So basically that would be this triangle and this triangle. So those two angles would be 3/4 pi and 5/4 pi. Now, those are the two solutions that we've memorized between 0 and 2 pi, but we also want to know between negative 2 pi and 0, how do we generate those other angles? We do that by subtracting 2 pi, or in this case, I will say subtracting 8/4 pi. So we subtract 8/4 pi from there, and we subtract 8/4 pi from there. Why aren't I subtracting 2 pi? because remember, addition and subtraction needed a common denominator, so we're going to put it with a denominator 4. So this one would be negative 3/4 pi, and this one would be negative 5/4 pi. And now we have all of the angles x between negative 2 pi and 2 pi, which have a cosine value of negative square root of 2 over 2, or negative 1 over square root of 2. Okay? All right. Here's one last simple one. Okay, this one's in degrees. So first of all, we're going to isolate sine x again. We're going to add 1 to both sides, then we get 2 sine x equals 1. Then we divide both sides by 2, we get sine x equals 1/2. What angles on the unit circle have a sine of 1/2? That would be these two low triangles, this one and this one. So that would be, and now we can work in degrees, so it would be 30 degrees and 150 degrees. Those would be the two angles that have a sine of 1/2. This is x and this is sine x. Okay. Now, we want all the solutions between negative 360 and 360. We memorized the solutions between 0 and 360, so we know we took care of 0 to 360. Now we need the angles between negative 360 and 0. So we just subtract 360 from each of these solutions, minus 360 degrees and minus 360 degrees, and we generate two more solutions that are these same two red triangles. Negative 360 plus 150 is going to be, I don't know, negative 210? Is that right? Yes. And then when we subtract negative 360 from 30 degrees, we get negative 330 degrees. Okay? So those are my four solutions that are between negative 360 and positive 360. Okay? We're going to use, these tables aren't really necessary in this case because they're so simple, but on the next page, we're going to use these tables for more complex problems, and then we'll see why they might be useful. Just like to mention one other thing before we head into the next section. Do you notice that we stopped adding or subtracting 360 because we looked like we were getting close to the boundary of negative 360 degrees, right? Since we got close, we stopped, right? It's good to know what the boundaries are at the top and the bottom of these intervals so that you know when you can stop adding and subtracting 360, okay? And in the next section, what we're going to do is we're going to look at equations where instead of just x here in the middle, you're going to have a transformed argument to sign, like, for example, 3x or x plus pi over 2 or something like that. So you're going to have a transformed input to sign. That complicates what the boundaries are, right? Because here we can just put the regular boundaries for x here, negative 360 to 360. But if we have 2x or something here, we need to make adjustments to these gray numbers, which are our top and bottom of the interval. So that's what we're going to work on in the next section. We're going to talk about how transformations inside the sine or cosine are going to change the boundary values. Let's take a look at page 4. Let's just look at the kind of problems we're going to have down here. Now, did you notice that sometimes inside the cosine and the sine, we're going to have a transformation? Okay, so when you have a transformation like this, how does that affect the domain that's given for x? Okay, so what we need to do is we need to translate our domain to see what angles are candidates to satisfy the equations. So, for example, if our original domain is 0 to 2 pi, what is our domain for if the input to sine and cosine is 2x? Well, we need to double all the angles, right? So 0 becomes 0, and 2 pi becomes 2 times 2 pi, which is 4 pi. So our new domain is going to be 0 is less than or equal to 2x is less than or equal to 4 pi. Okay? in the case of x plus pi over 2, we're going to translate these values also. So we're going to have x values of 0 to 2 pi. Those are the boundaries, right? And we're going to translate them to x plus pi over 2. So we're going to add pi over 2 to each one. So 0 plus pi over 2 is pi over 2. 2 pi plus pi over 2 is the same thing as 4 halves pi plus pi over 2, common denominator, which is 5 halves pi. If I wanted to write this in this form, I would write pi over 2 less than or equal to x plus pi over 2 less than or equal to 5 halves pi. So what I've done is I've taken this original domain and I've translated it to my transform domain. Okay. All right. I'm going to show you why this is useful in a second. All right. Next one. Now we have two steps. We're going to subtract pi over 4 from x, and then we're going to multiply it times 2. So that's like a double transformation, right? So now I think it's kind of easier to use the table. So first I'm going to start with x. Then I'm going to do the first step. I'm going to subtract pi over 4 from x. And then finally, I'm going to multiply that result times 2. Okay, so I'm going to do this to two values, the boundaries to my domain, 0 and 2 pi. So first thing I do is I do 0 minus pi over 4, and that gives me negative pi over 4. Then I'm going to take that value and I'm going to multiply by 2. And so that would give me negative 2/4 pi, which is the same thing as negative pi over 2. Now I'm going to do this process to 2 pi also. So 2 pi minus pi over 4, that would be 8/4 pi minus pi over 4, which gives me 7/4 pi. Then the second step is I'm going to multiply 2 times 7/4 pi, which gives me 7 halves pi. So now if I write it in an inequality, I would say my domain for this transformed input to the sine or cosine function is going to be negative pi over 4 less than or equal to 2x minus pi over 4 less than or equal to 7 halves pi. Okay. For the number 4, I have a domain for x ranging from negative pi to pi, and I want to know what's the transform domain for 3x. So basically, I'm going to have negative pi and pi for my x values. What happens when the domain undergoes the transformation 3x? I'm just going to multiply negative pi times 3 and multiply pi times 3. If I want to write, and that's it. If I want to write this in an inequality, I would write, okay, 3x and isn't in the interval from negative 3 pi to 3 pi. Okay. What about x minus pi over 2? So I'm going to put x here. I'm going to put x minus pi over 2 here. I'm going to put my two boundaries, which are negative pi and pi. In both cases, I'm just going to do a subtraction. So this would be negative pi is the same thing as 2 over 2 pi. If I subtract pi over 2, that gives me negative 3 halves pi. Pi is positive pi is 2 over 2 pi minus pi over 2. That gives me negative 1/2 pi, or negative pi over 2. Okay, so in this case, I would have x minus pi over 2 is between negative 3 halves pi and negative pi over 2. Finally, negative 2x. Okay, so my x value goes here, and then negative 2x goes here. My negative pi and pi values become negative 2 times negative pi, which would be positive 2 pi, and then negative 2 times pi, which just becomes negative 2 pi. Isn't that weird? It inverted it. So before it was from this one to this one, from negative pi to pi, and now it's the opposite direction. Okay, so negative 2 pi less than or equal to negative 2x is less than or equal to 2 pi. Okay, all right. Now let's do one example of a trig equation with an input which is transformed. Okay, so just to do our base function, let's look at the case that we're familiar with, which is, okay, you have cosine of x equals 1/2. We know that we want the domain to go from 0 to 3 pi, so I'm going to write those in gray. And if we're going to solve this equation, what we do is we think of all the solutions between 0 and 2 pi, because we have those memorized. So cosine x equals 1/2, that would be this triangle here and this triangle here. So that would be pi over 3 and, let's see, 5/3 pi. Those are the two triangles that we have memorized. Let's put those into our table. So we have x and we have cosine of x. If we, let's see, write down our two solutions here, pi over 3 and 5 pi over 3 are two solutions which lead to a cosine value of 1/2, right? Now we know that our boundary is from 0 to 3 pi. So are there any solutions between 0 and pi over 3? No, because we already know that we have all the solutions between 0 and 2 pi. But maybe there's a solution before we get to 3 pi. How do we find out? What we do is we add 2 pi to pi over 3, and we check to see if there's a solution which is between the two. And so if we add 2 pi to that, wouldn't that be 6/3 pi plus 1/3 pi? That would be 7/3 pi, right? Is 7/3 pi less than 3 pi? Yeah, because that's slightly more than 2 pi. Okay, so that's a possibility. Another possibility would be 5/3 pi plus 2 pi. Remember, 2 pi is 6/3 pi. 6/3 pi plus 5/3 pi is 11/3 pi, right? This is the same as 6/3 pi. 6/3 pi plus 5/3 pi is 11/3 pi. Is 11/3 pi less than 3 pi? 11 divided by 3 is more than 9 divided by 3. So 9 divided by 3 is 3 pi, right? So this solution is too big, right? 11/3 pi is bigger than 9/3 pi, so it's not a possible solution. So we're limited to 3 possible solutions, which are these 3 here. Okay, those are the 3 possible solutions. Okay, now that we did the cosine x problem, now we're going to do cosine of x plus pi over 3. Okay, so now we're going to have 3 columns. We're going to have x, we're going to have x plus pi over 3, and then last of all, we're going to have the cosine of x plus pi over 3. Okay, first let's put our boundaries. So our boundaries are going to be 0 and 3 pi. And 0 plus 3 pi over 3 is just pi over 3. And 3 pi plus pi over 3, let's see, that would be 9/3 pi plus 1/3 pi, so that would be 10/3 pi. Okay, so these are our boundaries. As we know, the two solutions that we've memorized for cosine of x equals 1/2 are pi over 3 and 5/3 pi. Now, in this case, if we put pi over 3 or 5/3 pi in for x plus pi over 3, then it would give us 1/2, right? So we don't want to put pi over 3 over here because pi over 3 is not an x solution for this. X plus pi over 3 is a solution. So one of our solutions is pi over 3, and the other solution is 5/3 pi. Basically, we're answering the question, what can I put in the parentheses to solve this problem? And the parentheses expression is x plus pi over 3. What angles can we put in there to get 1/2. And the answers are pi over 3 and 5/3 pi. Those are the ones we have memorized. Then we want to know, okay, but like what is that angle in terms of x, right? So we know that x plus pi over 3 would be pi over 3, but what would x be? So we're going to use the reverse translation here, because like to go from x to x plus pi over 3, we need to add pi over 3. If we want to go backwards to x, we need to subtract pi over 3. So we're going to subtract pi over 3, and we get 0, right? And then if we do the same thing with 5/3 pi, if we subtract pi over 3, we're going to get 4/3 pi. So let's check to make sure that works, okay? So let's test this first solution, x equals 0. If we put x equals 0 in for x, then we would get cosine of pi over 3. Cosine of pi over 3 is cosine of 60 degrees. Cosine of 60 degrees is 1/2, right? 1/2. Okay, so it worked. I can do that with 4/3 pi too. If I put 4/3 pi in for here, then I would add pi over 3 to it. It would be 5/3 pi. Okay, and 5/3 pi, cosine of 5/3 pi is an triangle, which would give us cosine of 1/2. Okay, so both of those worked. All right, now the question is, are there more solutions? Are these solutions okay? Now let's check. Is this in the boundary? It is, right? Pi over 3 is barely in the boundary. All right, so pi over 3 is okay. 5/3 pi is definitely between pi over 3 and 10/3 pi, so that one's fine. Now we start generating more solutions. How do we generate solutions? Remember, we are going to add 2 pi and add 2 pi. When we add 2 pi with a denominator 3, we're going to add 6/3 pi. So 6/3 pi plus pi over 3 is 7/3 pi. 5/3 pi plus 6/3 pi is 11/3 pi. Okay, 7/3 pi, is that between pi over 3 and 10/3 pi, the gray numbers? Yes, so this one is okay. What about 11/3 pi? No, that's too big. It went past 10/3 pi, so we don't want that one. What is the x value that corresponds to 10/3 pi in this translated domain? We're going to subtract pi over 3, right? Here we subtracted pi over 3. Here we subtracted pi over 3. Here we're going to subtract pi over 3 too. So we're going to get 6/3 pi, also known as 2 pi, right? Okay, so those are our 3 solutions. We know there's no more solutions because we know that we can't subtract 2 pi anymore because pi over 3 is already at the boundary. And we know we can't add 2 pi anymore because if we add 2 pi to 7/3 pi, it already goes over. So we need to stop, okay? So now we have 3 possible solutions, which are x equals 0, x equals 4/3 pi, and x equals 2 pi. Those are our 3 solutions